Hello everyone, my name is Pan. So today I'm going to talk about the human factor for telepresence. First, a little bit about me. I'm currently associate professor at Shanghai Jiao Tong University. Before that, I worked at Disney Research Los Angeles, and I received the master and the PhD in computer science from University College London. My research focuses on the virtual environment and computer graphic technology to advance character animation and avatar performance. Okay, here is the outline of today's talk. The COVID-19 pandemic and stay-home order have resulted in significant change in people's life. However, we note people still like to meet face-to-face for something important. This suggests that the video conferencing design may not sufficiently enough to match the user's need. In this course, we cover a few human elements that improve telepresence, as well as insights how the individual behaves and responds when using unique telepresence technology. Here are a list of the human factors that we will discuss in our course. First, the eye gaze. This is to see whether you are looking at a remote person or the remote person will give you a direct feedback. How does this will impact your teleconferencing experience? Next, the interpersonal trust. We will look at how to build the trust during teleconferencing experience, and will the mediated factor or display type will alter people's trust. Thirdly, we were looking at the physical embodiment. Will the physical embodiment change the people's behavior in teleconferencing? Then we'll look at the leadership effect, how to create different types of avatars, and how does this will change the way while people communicate with each other. Also, the engagement, how to improve the teleconferencing experience by improving engagement level. Lastly, we will see how to change the emotion factors. For example, how to build a more expressive and artistic avatar to representing the remote person. First of all, we were looking at the eye gaze. In terms of eye gaze, there's always been a problem in teleconferencing, mainly because of the two reasons. The first reason is because of the parallax effect. That is, when we're looking at the camera, the remote person will feel like they were looking at them. However, if we're looking at the screen, we will lose the connection with the remote person. That is normally because the camera is on the top of the computer. However, the remote eye position is on the center of the screen. And another problem is because of the Mona Lisa effect. This is normally happen for the multiple person. For example, if you look at the picture of Mona Lisa, no matter how you rotate your head, you will feel like that she is looking at you. And also for the Uncle Sam on the right side of the figure, you will feel like the Uncle Sam is pointing at you all the time, no matter how you're changing your position in front of the screen. This is normally because of the 3D figures turn into the 2D image. A lot of the information has been lost. It's not only getting loss of the eye contact and the gesture informations, and if for the something important such as surgeries, we cannot point into the correct directions. That causes a huge problem for teleconferencing. So to solve this issue, we developed a couple of the novel displays, which I'm going to introduce one by one. This is a work done from 2010 to 2014 at Beaming project, which with the aim of to give the remote person telepresence in the local room, and the remote person act as if they were located in the local room. So my responsibility on this project is to building 4 novel displays to represent the remote person. And here is the overview of the display I have been built and how they improve the telepresence experience. The first one is eye gaze, and although the display has improved the eye gaze, and some of them only support single users, and some of them supporting multiple users, and some of them even support stereo views. And as the situated display, they can provide 360 views for that. Note that this is different from the virtual reality technology, as we don't need to wearing headset to creating this to representing remote person. Okay, I'm going to go through each of these displays and talk about how this helped to improve the telepresence experience. Okay, our first example is a spherical video media display. First, we use the array of the camera to capture the remote person, and those array of the videos was streamed to the local room. Depending on the local observer's position, we select the correct view and finally present it on the spherical display. And here is an example of how we actually rendering it. We use a couple of the computer graphic techniques, such as projective texture, cube mapping, and finally we present those remote person's image on the spherical display. Our spherical display have a couple of the highlights. Because the spherical display offers 360-degree view, however, the flat display can only visible from a front. So we can actually situate this spherical display inside the room. Secondly, by using a surrounding camera array, which allows one principal observer to accurately tell where the remote person is looking at from multiple observing positions. Our second example is a cylindrical display. We use the array of the camera to capture the remote person, and the array of the projector to represent each of them onto a cylindrical screen. This cylindrical screen reflects each image to a very narrow viewing zoom without crosstalk. So it allows multiple observers to see the perspective correct image of the remote person from multiple viewing directions simultaneously. We also run a user study to demonstrate the effectiveness of our cylindrical display. Our results has demonstrated our system can supporting observers to better tell where the remote person is looking at. Okay, our next example is a random hole multi-view display. This is different from traditional parallax barrier display, where they use a lot of the parallax line to separate the left eye and the right eye's image. The traditional parallax barrier only supports the viewer at a specific viewing position. The highlights of our system is to randomize those holes so that viewer at any arbitrary location can see a 3D view. Here is an example of our random hole rendering results. We're supporting multiple perspective correct stereo view in arbitrary location. And we run a user study to demonstrate the effectiveness of our system. It allows multiple users from multiple viewing positions to simultaneously tell where the remote person is looking at. We also found motion parallax provides a dominant effect in improving effectiveness of user estimates the gaze direction. Also, additional effect for the perspective correct augmented by the 3D view. Okay, after the eye gaze, let's move on to our next topic, which is interpersonal trust. As we know, trust plays an important role for the communication. Sometimes it even enables for effective communicate. If you don't trust someone, you probably don't want to have a conversation or even talk to them. In telepresence, as a mirroring of trust, a popular experiment model currently used by the researcher is called social dilemma games, such as the day trader games. Those social dilemma games, varying how difficult they are depending on exactly rules and payoff structures, but it generally takes some amount of the time and some communication in order to reach certain level of the trust so that people would like to collaborate with each other. However, those social dilemma games are normally good model for two-way conversations. For evaluate a one-way conversation such as our system, we propose the trust game models. We're marrying the participant advice-seeking behavior under risk as an indicator of the trusting in that advisor. Here is how we did it. We used the Who Wants to Be the Billionaire games. We asked the participant very difficult questions. For example, which subject did Bill Gates actually study at Harvard? These questions were very difficult where participants don't know the answers, but they can ask for the advisors. We're providing participants two advisors. One of them was expert, another was a non-expert. But the participants don't know who is expert and who is a non-expert. The participants have to observe their interpersonal clue so that they decided which advice whether they would like to ask. Here's how this worked. The trust is normally arised under the risk and uncertainty. Here the participant don't know the advisor's ability and their motivations. They have to observe from their interpersonal clues how the viewing angles and display type actually interference participants' observing results. So this can be an indicator of how the display type or viewing angle would interfere the participant's trust behavior. And here we developed a spherical avatar mediated display to show the trust can be actually altered by display type. Our displays we use a Kinect to track the people and then we're presenting an avatar on the spherical display. We run an experiment comparing our spherical display to the flat display. We actually found participants were able to discriminate trustworthy and least trustworthy advisors irrespective of display type. However, a negative bias for the flat display can interfere with the user's ability to discriminate effectively. This shows trust can be easily and significantly manipulated in the mediated interaction by adjusting display viewing angles. Next topic, we will look at the physical embodiment in telepresence. Here we introduce the two robots. One of them was located in USA, and another one was located in the UK. The robot located in the USA is representing the user at the UK, while the robot located at UK was representing the user at the USA, so that two people can interact with each other with some physical embodiment factors. We're looking at, does the robot we're going to help the teleconferencing? There were a couple of the features that the robot have comparing to the avatar-mediated communication or video-mediated communication. First one, the physical embodiment. There were actually something standing behind of you, and this can give you a sense of the physical embodiment might going to improve the trust. Another factor is the physical contact, that this robot can actually touching you or shake hands with you. But some researcher was suggesting, like, if the robot was touching you, they actually make you scared. if it doesn't feel good. Or sometimes people feel like if they're having a handshake before the conversation, this actually going to increase the level of the trust. Also, the robot have a problem with the motion fluency comparing to avatar-mediated teleconferencing and video-mediated conferencing. The next one, the robot is similar to the avatar, has a mask identity. The remote person cannot tell the local person who they are comparing to the video-mediated communication because they can actually see the identity of the remote person. And the last feature of the robot is they actually giving us a 3D crew. This is similar to the avatar if they were presenting on the 3D display or virtual reality system. However, the video system can only provide 2D crew. Of course, the 3D video can provide in 3D crew, but here we're talking about the 2D video. So we run a user study to see how does the robot going to influence mediated communication? We're comparing it with the avatars and the videos. We used our trust model to evaluate the system. We used the robot, video, or avatar to representing the advisors. We evaluate participant advice-seeking behavior under the risk as an indicator of their trust in that advisor. Our users' trust assessment shows both the robot and the video achieve similar level of the trust. However, the avatar achieves the lowest level of the trust during the interaction. This reveals the physical presence of the robot representation might compensate the lack of the identity crew in terms of the interpersonal trust. Okay, next we look at the leadership effect. First, I'm going to give you an example of what it is, the leadership effect. This normally happened in the collaborative mixed reality or collaborative virtual reality system, or nowadays a popular name called the metaverse, where multiple persons will come across together in shared virtual environment, and each of them was representing them by a self-avatar. Let me give you an example. If the couple of the students would like to collaborate together in the virtual environment, one of them was dressing up themselves as a professor for their avatars, while another person was still dressed themselves as a student. While they're doing a collaborative task, the person embodied themselves as in the professor avatars would automatically become a leader during collaboration. And this also happened for the different level of the immersion. For example, some of the people was using virtual reality system to do a collaboration, while another person was using a desktop to control the virtual avatars. The person who with higher level of the immersion would more likely to become a leader during collaboration. And in our case, we compare 4 scenarios in the mixed reality system. The first scenario is a co-located AR to AR system, which 2 people was collaborated together in a mixed reality system. A second scenario is AR to the virtual reality system with a virtual body, where the AR scenario, the remote person was representing themselves as a virtual avatar. And the next scenario is AR to the virtual environment without a virtual body, where the remote person representing themselves just using controllers. And the last one is AR to the desktop scenario, where the remote person using desktop to control the interactions. In these 4 scenarios, the people have a different level of the immersion. The first one is 2 persons have a same level of immersion, which served as the baseline of our study. And we found the more immersive the participant would like to single out themselves as a leader. We also found there was no leadership effect in the AR to AR scenario. This is understandable because the 2 sides was balanced. And we also found there was no leadership effect for the AR to the virtual reality system with a virtual body. And this is also kind of understandable because they still have a full body avatar to represent themselves. However, we do find leadership effect in the AR to the VR scenario where the VR scenario people only use the controller to control themselves, which has a less level of the immersion. And we have an even stronger leadership effect in the AR to the desktop computer, where the participant controls themselves using desktop. And from this study, we also found the leadership effect only emerged in the 3D interaction, but not in the 2D interaction. This is quite understandable as well, because in the 2D interaction, people share the same level of the interaction techniques. The leadership effect is interesting because it actually alters the people's behavior in the metaverse or collaborative virtual reality. So people can dress themselves into different avatars and to achieve certain levels of goal. Next, we talk about users' engagement. The engagement is also another important factor for telepresence, which will attract more attention for the remote persons and getting a better result for conversation. By engagement, we refer to the process of being participant establish, maintain, and end their perceived connection. The audience look at a performer less than normal. The audience rated less engagement. Therefore, the duration and frequency of the glance dictate towards the speaker will be considered indicative of the audience engagement level. Here we set up an adaptive dynamic anamorphic system as an example. The highlights of our system is it improves one of the VIP users' viewing experience without sacrificing another guest's viewing experience. Here is how we do it. First, we're rendering one of the primary characters in the scene depending on the VIP user's position. We render this from perspective correct view. While the person was moving, the character's rendering position is moving as well. Then we render the background object and the characters and everything from normal view. Next, we create the mask used for composition. Finally, we get our results. So the background stuff was rendering from the normal view, while the primary character was rendering from perspective correct view, depending on the VIP viewer's position. We run the experiment to demonstrate the effectiveness of our system as well. We found the VIP guests results in improved gaze and estimation and engagement estimation. And this performed without sacrificing another guest's viewing experience. This is particularly useful for the theme park as well, because those displays will improve one user's viewing experience while another person can still enjoy the show. Lastly, we talk about emotion. Here, we particularly focus on how to represent a remote person in stylized character. There were lots of motion capture software such as ERKit or FaceWare can capture the remote person and representing them in the avatar. However, if you look at the second line here, those stylized character can only create the geometry information, but fail to address essential issue of producing clear expression that can be correctly identified. This is primarily owing to geometric markers are not adequate enough for facial expression transfer. Also, the geometry markers and feature model are normally developed for the human faces instead of stylized character faces. Additionally, it's very difficult to use motion capture software to produce expressive and artistic-like stylized character facial expression. So we developed a facial motion capture with a live mode dynamic system called MyCap. Our goal is to improve the performance-based animation, which can drive believable stylized characters that are truly perceptional. By combining traditional blend shape animation techniques with the machine learning models, we present a real-time motion capture system, which can drive characters' expression in a geometrically consistent and perceptually valid way. Here's how it works. The first slide here is the traditional real-time motion capture pipeline. For example, if we use the ARKit, we create 41 blend shapes, and then we use a FaceLab Link or similar software to get the blend shape weight, and finally drive the characters. But before driving eventual characters, we add in a machine learning model called blend shape adaptation model. The blend shape adaptation model, we use a blend shape weight, and we also use the output will be controller values. We find a relationship between the blend shape weight and the controller values, which is based on the data set created by artists, so that eventually can drive the expressive and artistic-like character expressions. Then we add the multi-character adaptation models. These models, the input data will be primary characters controller value, and output data will be the secondary character controller values. We also use artistic created character rig parameters to train the dataset. So our MyCap system actually combines the blend shape animation technique and the machine learning models. This is the first real-time system that transfers the human expression to multiple stylized characters in a geometric consistent and perceptually valid way. Another highlight of our system is that we don't need to create each set of the blend shape for each new characters, which also need significant amount of the time. Okay, here we come to conclusion. In this talk, we discussed several human factors to improve teleconferencing experience. First, we look at eye gaze and giving us 3 examples to help improve the eye contact in teleconferencing for single user, multiple user, and for a 3D view. Then we talk about interpersonal trust, and we also show a spherical display that can alter the people's trust by comparing to the flat display. Then we talk about the physical embodiment. We give the people examples as a one-way conversation and two-way conversation scenario. Next, we talk about embodiment and the level of the immersion by giving an example of the mixed reality system. We talk about users' engagement by showing people dynamic, adaptive, and morphic system. Finally, we discuss how to represent a character's emotion for the remote person. Together with those demonstrations, this will be helpful to design future teleconferencing system. And here is the selected reference for today's talk. Thank you very much for listening. Feel free to drop me an email if you have a question.